Welcome to the Explainer. Today we're going to pull back the curtain on something you use every single day, but might not think about: your computer's memory and storage. We're going to get into the nitty-gritty of how your machine handles all its data. So, let's dive in.
Have you ever been shopping for a new computer, looked at the specs, and thought to yourself, wait a minute, why does it have memory and storage? Aren't they basically the same thing? You're not alone in wondering that, and the answer reveals this really clever piece of engineering that's at the heart of pretty much every digital device we own.
Okay, so on the surface, the difference seems pretty simple, right? You've got memory, which we usually call RAM. It's your computer's short-term workspace. It's super fast, but it's also volatile, which is just a fancy way of saying it forgets everything the second you turn the power off. Then you have storage, like your hard drive. That's the long-term stuff. It's slower, but it holds way more information, and it remembers it all even when the power's off. But the real question, the big aha moment, is why? Why does it have to be this way?
Well, it all comes down to a classic engineering problem. A puzzle, really. It's sometimes called the memory trilemma. See, when you're designing a system to store data, you're always trying to balance three things that are constantly fighting each other: speed, capacity, and cost.
Look, if we could just wave a magic wand, we'd create one single type of memory that does it all. It would be incredibly fast, it would hold a massive amount of data, and it would be super cheap. But back in the real world, the laws of physics and economics have something to say about that. The rule is you can pick any two of those qualities. You want it fast and with a huge capacity, it's going to be crazy expensive. You want it cheap and with a huge capacity, okay, but it's going to be slow. This trade-off is the absolute bedrock of how your computer is designed.
To really wrap your head around just how different these speeds are, let's look at the numbers. The absolute fastest memory in your computer, the stuff that's practically welded to the processor's brain, is called cache. Accessing it takes about 10 nanoseconds. That's 10 times billionths of a second. It's a timescale that's just hard for our brains to even process.
Now, compare that to your good old-fashioned spinning hard disk. To get a piece of data from that thing takes around 10 milliseconds. Now, that sounds fast, right? Milliseconds? But here's the thing, it is 1,000,000 times slower than the cache. Let me put that in human terms. If accessing the cache memory was like snapping your fingers, then waiting for the hard drive would be like waiting for almost 3 hours. That's the difference we're talking about.
And this brings us right back to that fundamental trade-off, which you can see perfectly in this pyramid shape. As you go up the pyramid, things get way faster, but they also get way more expensive for the amount of space you get. As you go down, things get slower, but you can afford to have tons and tons of space. You just can't have the best of all worlds in one single technology.
So, what do? If you can't have one perfect type of memory, what's the workaround? Well, the solution engineers came up with is just genius. They decided, hey, instead of picking one, let's build a team. And that is the whole idea behind the memory hierarchy.
And the goal of building this team, this whole hierarchy, is to pull off a neat trick. You want to create a computer that to you, the user, feels like it has really fast memory, but is built with a total cost that isn't astronomical. It's about getting the performance of the expensive stuff with the affordability of the cheap stuff, all by using them together in a smart way.
A great way to think about this pyramid is like an office. Right at the very top, you have the CPU registers. Those are like the thoughts inside your head. Instant access. One level down is your RAM. That's your desk. It's where you keep the papers and tools you're working on right now. Further down is the hard drive. That's the big filing cabinet across the room. It holds everything, but you have to get up and walk over to get something. And way at the bottom, you have things like tape backups. That's like an off-site warehouse. The data is safe and stored cheaply, but it's going to take a while to go get it.
All right, so let's actually take that tour down the pyramid. We'll start at the top and meet the different members of this memory family. The top couple of layers are what we call primary memory. This is all semiconductor-based, meaning it's pure electronics. There are no moving parts. That's why it's so fast. The CPU can talk to it directly. And the main thing to know about this stuff, especially RAM, is that it's volatile. When the power goes out, poof, anything stored there is gone.
Now, even in this primary group, there are a few important flavors. You've got RAM, random access memory. That's your main rewritable workspace. Then you have ROM, read-only memory. that's non-volatile, and its data is burned in at the factory. It holds the super basic instructions for how your computer even starts up. And then there are variations like PROM, which you can program yourself exactly one time, but you can never erase it.
So let's move further down the pyramid to what we call secondary memory. This is your long-term storage, your digital filing cabinet. It's non-volatile, which is crucial. It means your photos, your programs, your documents, they're all safe and sound when you shut the computer down. This is where you find things like hard drives.
And it's kind of wild to think about what's actually going on inside one of those old-school hard drives. It's this incredible, tiny, mechanical ballet. You have this arm with a read/write head on the end, and it's flying just a few nanometers above a metal platter that's spinning thousands of times a minute. It's locating and changing these microscopic magnetic spots that represent your ones and zeros. The precision is just mind-boggling.
And this brings up a really important distinction. RAM gives you what's called random access. That means the computer can jump to any piece of data anywhere in the RAM in pretty much the exact same tiny amount of time. But some other types of storage, like old-school magnetic tape, use sequential access. Think of a cassette tape. To hear a song at the end, you have to fast-forward through all the songs before it. It's the same idea. That's why tape is mostly just for backups these days.
Okay, so that's the tech tour. We've met the whole family. But what does all this geeky stuff actually mean for you? You know, sitting at your computer, trying to get work done or play a game. Why should you care about any of it? Well, here's where the rubber meets the road. I bet you've experienced this, or at least heard someone talk about it. You take an old computer, you pop in some more RAM, and suddenly the whole thing just feels snappier, more responsive. Why? What's actually happening there? It all comes back to our hierarchy. Let's go back to our office analogy. Adding more RAM is literally like getting a much bigger desk. If you have a tiny desk, you can only have one or two things out at a time. For anything else, you have to get up, walk over to that slow filing cabinet, find the folder, and bring it back. With a huge desk, you can have everything you need spread out right in front of you. More RAM means your computer's processor spends way more time working and a lot less time waiting.
And the reason we want to avoid those trips to the filing cabinet as much as possible is something called access time. For a mechanical hard drive, that delay isn't just one thing. It's the sum of two different physical movements that both take up precious time.
First, you've got what's called seek time. That's the time it takes for that physical arm to swing across the platter and position itself over the right circular path, or track. Then, once it's there, you have to deal with latency time. The arm has to just wait there as the disk spins around until the exact chunk of data you need is directly underneath it. Both of these physical delays are what make hard drives feel like they're moving in slow motion compared to the purely electronic speed of RAM.
Now, to fight this slowness, engineers came up with some clever tricks. One of the big ones is organizing data into cylinders. If you have multiple platters stacked up, a cylinder is just the set of all the tracks that are in the same position on each platter. By storing related data in a cylinder, the drive can read a whole bunch of it without having to move the arm, which is the slowest part of the whole operation.
So let's bring it all home. The reason your computer has both memory and storage isn't a bug or some weird design flaw, it's absolutely a feature. It's this brilliant, invisible system of trade-offs, this carefully balanced team that makes our digital world possible. It lets us have computers that feel lightning fast, but can still affordably store a lifetime of photos, music, and memories.
But I'll leave you with a final thought to chew on. Modern solid-state drives, SSDs, they're a game changer. They're non-volatile, like a hard drive, but they're made of semiconductors, like RAM. They don't have moving parts. And every year they get faster and cheaper. They are seriously starting to blur the lines between that fast desk and that slower filing cabinet. So you have to wonder, is this elegant pyramid that has defined computing for decades about to get completely shaken up? Something to think about. Thanks for joining me on The Explainer.